Hi there! In this video, we're going to be going over the 3 review problems in the Semester 1 final review for AP Physics. And I'm going to be starting off with number 1. The problem gives a diagram of a block on a surface, and the coordinates are already chosen for us. Anything that moves to the right is a positive x direction, anything that moves up is a positive y direction. And this problem gives an 8 kilogram block is being pushed with an applied force of 21 newtons. The first part, part A, draw a free body diagram. On a free body diagram, you are considering the system, in this case, the block, and the earth. And to draw a free body diagram, I'm just going to copy down what has already been given. So the surface and the block. The earth is pulling that block down because it has mass, so there's a force of gravity. Opposing that force of gravity to keep the block stable in the y direction is a normal force. And these two are actually balanced because I can tell right away that the block isn't accelerating in this positive or in this y direction at all. So I'm going to represent that by drawing my force vectors on my free body diagram as equal in length. And the problem says that there's an applied force on the block of magnitude 21 newtons. And it doesn't exactly say which direction, but I'm just going to call it. I'm just going to say this way. There's an applied force. There's no mention of friction, so I'm going to leave the force of friction out of my free body diagram. However, if friction were explicitly mentioned in that first part, then I would add a force of friction that's smaller than this applied force, going in the opposite direction. This applied force is going to cause the block to move, and so friction is a force that opposes motion, so the friction force would be going that way. Moving on to part B, find the acceleration in the y direction. I kind of already talked about that. Because the block isn't moving or accelerating in the y direction, the acceleration in the y direction is 0. Part C, the acceleration in the x direction without friction. So we're assuming that this is a frictionless surface. So to find acceleration in the x direction, remember this is the positive x direction. Let's squeeze that in there. I have to consider, in order for me to find the acceleration in the x direction, I have to consider all the forces acting on it in the x direction, because if there aren't any forces, or if I don't consider the forces and no other information about its motion is given, then I don't really have much to work with to find out what the acceleration is. So I'm going to use Newton's second law that says that the net force on any object in one direction is equal to the mass times acceleration. In the x direction, we only have, because the problem explicitly said to ignore friction, we only have this applied force as a force acting in the x direction. And I'm just going to list off what has been given. It's an 8 kilogram block, and applied force is 21 newtons. So I could just plug these in. So the applied force is 21, the mass is 8, and I'm trying to find out what x is, or what acceleration is. And this gives me about 2.62 meters per second squared. Okay. Moving on to part D, how far does it travel in 11 seconds, assuming it starts from rest? So there's giving me a piece of information here. That initial velocity is 0, and the time that passes is 11 seconds. And we want to know how far it travels. So that's a displacement, that's a change in position. So I have my acceleration in the x direction and the y direction. And I can tell that they're talking about displacement in the x direction because forces in the y direction are bound, so there's not going to be any motion. But in the x direction, we can find we can find displacement by using one of the kinematic equations. And looking over my equation sheet, using what I know to figure out what I don't know, I think the best thing I can use is this one right here. So to find out what the change in position is, I could plug in what I know about initial velocity and time and acceleration. By the way, if I were to go back to part C and give this final answer as my final answer, I want to make sure that I have the appropriate sig figs. In this problem, the minimum number of sig figs, all the quantities were given to 2 sig figs. And so my final answer actually would be 2.6 for part C. For the sake of solving for this change in position, I'm not restricted by sig fig, so I actually want to keep the number to something more than the sig figs required in their final answer. So I'm going to use this 2.62. Plugging that into my calculator, I find about 158.51 meters. And going back to what I said about significant figures, changing this number to 2 significant figures would actually look like 160 meters. All right, part E, what is the velocity after 11 seconds? This is another problem that I can solve using a kinematic equations. So final velocity after 11 seconds. So if I know final velocity, or if I want to know final velocity, and I know the time, the initial velocity, and the acceleration, this equation is going to help me out. It starts from rest, its velocity is 2.62, and it's 11 seconds. And that equals 28.82 meters per second. To 2 sig figs, my final answer will be 29. All right. Part F and G. G is a little bit of a typo going on there. After 11 seconds, it slides onto a surface with coefficient of kinetic friction of 0.14. What is the acceleration in the x direction? So this introducing a rough surface or some kind of surface that isn't frictionless means that now the net force in the x direction has to include a force of friction, and that the direction of that force of friction, as I mentioned, is opposing the motion. So to help me solve this problem, I actually want to, I'm going to need that in a second, but I'm actually going to want to draw a new free body diagram that includes that force of friction. So there's my force of gravity, here's my normal force, here's my applied force, and there's a friction, a very small friction force. That's not what we're trying to find. We're trying to find the new acceleration. So using the same steps as that previous part, I'm going to consider all the forces acting in the x direction in order to find out what that acceleration is. So now we have applied force, which is in this positive x direction. I'm going to set my coordinate system so I remind myself and I stay consistent, minus this friction force. The applied force was 21 newtons, and the formula I use for the force of friction is mu times the normal force. Mu is given as 0.14, and remember there's no units to mu, it's just a ratio. It tells us by how much the force of friction affects a sliding object with respect to the normal force that that object has between the surface and itself. So in order for me to complete this, I'm going to need to know what the normal force is. I mentioned in the first part that since it's not accelerating in the y direction, this normal force and this force of gravity must be balanced. So the normal force and the force of gravity are equal to each other. Normal force, therefore, is mass times g. It's an 8 kilogram mass, and 9.8 is the acceleration due to gravity. And I can tell that that's going to be a positive force because it aligns with the coordinate system that was set. So the net number is 78.4 newtons. Okay. So 21 minus 0.14 times 78.4 is equal to the mass. I'm just going to go ahead and plug in 8 times acceleration. This is 21, and multiplying these two together get me 10.98, and that's equal to 8a. So now I can combine these terms. I get 10.02 is equal to 8a, and a is now 1.25, which is much slower. It makes sense that this is a lesser number than what we got in the first part, or that part C, which is 2.62. So it was going much faster without friction. That makes sense. Okay, moving on. The last part, how far does it travel after 15 seconds on this new surface? So for this, we got to be careful because once it entered that new surface, it had some velocity. So this time we cannot consider that it starts from rest. So its initial velocity as it enters this new surface is from that last part, which is 29. And actually I'm going to use that 28.82 just to be safe. And I'm told the amount of time that passes, 15 seconds, and I have my new acceleration right up here. This is part H. And what we're trying to find is how far it travels. So what's delta x? So I'm probably going to use the same equation from the previous part where they asked us the displacement on a frictionless surface. And now I have 28.82 as my initial velocity, plus 1/2 my new acceleration, and then 15 squared. So the numbers I'm getting are 432 plus about 140.6. Adding those up comes out to be about 570 meters.